Okay, today I'll take a look at applications of rational equations in the context of word problems. Some of the more important problems that you'll see on like the SAT or the ACT. So I'll go over two of the more important type of word problems related to rational functions or rational equations. So let's take a look here. The first example 3, involves an application of using the distance formula. So again, to recall, distance is equal to rate times time, or distance, how far you travel, is equal to how fast you go. So rate times and how long you travel at that rate. So distance equals rate times time. So for example, if you're traveling at 60 miles per hour and you travel 2 hours, then you've traveled a total of 120 miles. So distance equals rate times time. I could also express the same equation in terms of t. So if I divide both sides by r, then distance divided by rate will equal time, or d over r equals t. And this is going to be important for this application here. Okay, so here we have a kayaker is spending an afternoon paddling on a river. This kayaker, she travels 3 miles upstream and 3 miles downstream. So go 3 miles up and then 3 miles down. Now, she spends 4 hours in total traveling up and downstream. Okay, so this is upstream and then this is down. Total 4 hours. In still water, in other words, with no current, the kayaker can travel at an average rate of 2 miles per hour. So the rate is 2 miles per hour in still water. Based on this information, and what was the average speed of the river's current? Okay. So what we're looking for is to determine what was the current of the river when she traveled upstream. She was going against the current. And then what was the current of the river when she traveled downstream? She was traveling with the current. It's like riding a bike. You ride your bike into the wind, or you can ride your bike with the wind behind you. So let's take a look at this problem here. Okay, so let's take a look at the important points. The kayaker spent a total of 4 hours kayaking. She went 3 miles upstream and she went 3 miles downstream. And the average speed in still water, that is with no current, is 2 miles per hour. Okay, so the distance upstream is 3 miles. Now, if you're traveling upstream, you're traveling against the current. So your rate or your speed is going to be lower. That's for sure. If you've ever ridden your bike into the wind, you know your rate is going to be a lot less than riding your bike with the wind behind your back. So going upstream, the kayaker travels 3 miles, but the average speed is going to be less than what the speed would be in still water. So the average speed is we'll say it's going to represent 2 minus c. C representing the speed of the current, which we don't know. But we know that the average speed will be less than the still speed of 2 miles per hour. A still water speed of 2 miles per hour. Our average speed is going to be less. So we say 2 minus C. Well, distance divided by speed or rate equals time. Okay, so again, distance divided by speed or rate, or we can say distance divided by speed or rate equals time. Okay, so distance 3 divided by 2 minus C will be the time. So again, this is D, this is S, and this is T. So 3 divided by 2 minus C will be the time she spent traveling upstream. And now traveling downstream, she's traveling not against the current, but with the current. She's going to travel much faster. She's still going to travel 3 miles, though, downstream. But her rate should be faster than the average speed in still water. So her rate should increase because she's traveling with the current. So her rate is going to be represented as 2 plus C. And then the time that she spent traveling downstream will be, again, D divided by S is equal to T. So her rate is going to be, or the time will be 3 divided by 2 plus C. Traveling down and then traveling up is 3 divided by 2 minus C. So we know that the total time she spent was 4 hours traveling up and down. Okay, and so what we want to do is we want to determine, well, how many hours did she spend traveling upstream? And how many hours did she spend traveling downstream? But we've already determined that with the equation. The time traveling upstream is 3 minus 2C. And then the time I'm traveling downstream is 3 divided by 2 plus C. So again, time up is 3 divided by 2 minus C. And then time spent traveling downstream is 3 divided by 2 plus C. So we have the equation in total time equals 3 divided by 2 minus C plus 3 divided by 2 plus C. Right. And so now all we have to do is solve for C to find what is the speed of the current. And so this is a problem like we solved yesterday. We want to eliminate the least common denominator. So my least common denominator is going to be 2 minus C times 2 plus C. Okay, so 2 minus C times 2 plus C. Well, if I follow that, that's the difference of squares, and that's going to be 4 minus C squared. Okay, so when I multiply my entire equation by my LCD, which is 2 minus C times 2 plus C. Okay, so what I'll do is I'll multiply 4 minus C squared times 4, and that will equal, and again I'm multiplying by my LCD, which is 2 minus C times 2 plus C, but I can also represent that as 4 minus C squared. Now why did I use 4 minus C squared? When I multiply by 4, it's just going to be less work when I multiply by 4. And then I'll take 2 minus C times 2 plus C, and I'll divide that by 2 minus C, and that will leave me with 3 then. So this will leave me then with 3 times 2 plus C. Plus, and then plus 3. And when I take 2 minus c times 2 plus c and divide that by 2 plus c, that will leave me with 2 minus c, so I'll have 3 times 2 minus c. So there you go. So I eliminated the denominator. Now all I have to do is multiply. So 4 times 4 is 16, so minus 4c squared equals 6 plus 3c plus 6 minus 3c, and so this is going to equal 12. 16 minus 4c squared. And then let's see here, if I subtract 12 and add 4c squared, I'll have 4 equals 4c squared. Subtract 12 and add 4c squared to both sides. And then, solving for that, if I divide both sides by 4, I'll get 1 equals c squared, and then take the square root of that. I'll get plus or minus 1, but negative, so I'll get plus or minus 1 equals c, but in the context of this problem, the current can't be negative, so the current was 1 miles per hour. Okay. Yeah, so there. So the current was 1 mile per hour. So when traveling upstream, okay, she's 2 minus 1. So she was traveling upstream at 1 mile per hour, but then traveling downstream, she was traveling at 3 miles per hour. Okay. So one of the classic problems involving solving word problems and rational equations. Now let's take a look at another one of the problems involving rational equations. Another one is when it involves work, and you see this quite often on the ACT or SAT. So imagine that you cut the grass, you cut your mom or dad's lawn, and you do it in an hour or 60 minutes. Okay, so your rate is 1/60th of an hour. Okay, so again, you cut the grass and you can mow the lawn in 1 hour or 60 minutes. So your rate is 1/60th of a minute then is your rate. So 1/60th of a minute. All right, and so in 60 minutes then, if your rate is 1/60, that's your rate per minute, then in 60 minutes you will have completed the entire job. So 1/60 times 60 is 1. In 30 minutes then, if you can mow the lawn in an hour, in 30 minutes you will have completed 1/2 of the job. Okay. In 50 minutes, then you will have completed 5/6 of the job. Right? So that's how these work problems work applications is what we call them. Okay, so keep that in mind. Also, this year, if you can mow the lawn in 1 hour, and let's say here, your buddy can also mow the same lawn in 1 hour, then working together collectively, you should be able to mow the lawn in 30 minutes, right? If you can mow the lawn in 1 hour and your buddy can mow the same lawn in 1 hour working together, you should be able to mow the lawn in 30 minutes. Okay. Yeah. Now, if you can mow the lawn in 1 hour, but your buddy can mow it in like 1.5 hours, so your buddy is a little slower. Working together, then you would expect that the time it would take you would be more than 30 minutes, because if your buddy can mow the lawn in 1 hour and you can mow the lawn in 1 hour, and working together, you should be able to mow the lawn in 30 minutes. But if your buddy is working slower than you, then working together, you would expect to be able to mow the lawn collectively in more than 30 minutes because your buddy is working slower than you are. And then likewise, if your buddy can mow the lawn in 1/2 hour and you can mow the lawn in 1 hour, then working together, you would expect that you guys would be able to mow the lawn in less than 30 minutes because your buddy's working faster than you. So that's how these work application problems work. So just keep that in mind. So here we go. So Jason can clean a large tank and an aquarium in about 6 hours. So Jason's rate of the tank per hour then is going to be 1/6. Okay, so Jason can he can clean the tank in 6 hours, so 1/6 of an hour. So and then in 6 hours, he will have completed the entire job. Okay, so Jason can clean a large tank in about 6 hours. Now, when Jason and Lacey work together, they can clean the tank in 3.5 hours. Well, apparently Jason is working, or Lacey takes longer to clean the tank than Jason does. Because if Lacey could also clean the tank in 6 hours, then working together, they should be able to clean the tank in 3 hours. So apparently Lacey is working a little slower. Okay, so what we want to do, so when Jason and Lacey work together, they can clean the tank in 3.5 hours. Okay, so Jason's rate is 1/6 of a tank per hour, and then Lacey's rate is what we don't know, so we say is 1/8 of the tank per hour, where H is the number of hours needed to clean the tank by herself, so that would be Lacey's rate. Okay, so what we know is that Jason can clean the tank in 1/6 of an hour, but collectively, working together, they clean the tank in 3.5 hours. So working together, they should be able to complete the entire job, or one complete job would equal 1. Just like if Jason was working just by himself, and his rate is 1/6 of an hour times 6, then in 6 hours, he'd be able to complete the entire job. 1/6 times 6 equals 1. Okay, but Jason and Lacey, they're working together. But they can, in working together, it will take them 3.5 hours. So Jason's rate, again, is 1/6, but they're working together, so this is, we're going to multiply by 3.5, and then plus 1 over H, which is Lacey's rate, and times 3.5, because that's how long it takes both of them to work together. Okay, and so we have, all right, and so what we have here, if I just read it like this, I have 3.5 over 6 plus 3.5 over H, and that equals 1. Okay, my LCD is going to be 6H, right? Yep. So when I distribute the 6H, then 6H divided by 6 will be H, and H times 3.5 will be 3.5H, plus 6H divided by H is going to be 6, and then 6 times 3.5 is going to be 21 equals, and then 6H divided by 1 is 6H, and 6H times 1 is going to be 6H. Okay. So we have 3.5H plus 21 is equal to 6H. And then we solve when we get 8.4 hours. So, and like I said, it was apparent then that Lacey was going to take longer than 6 hours because working together, it took a total of 3.5 hours. Had Lacey worked as fast as Jason, they would have been able to finish in 3 hours. Okay, so then it takes Lacey by herself 8.4 hours to clean the tank. So 8 hours and 24 minutes. So again, all of these work applications, they work like that. And on the right, we always have 1 because we're completing one job. Okay, so 2 of the more important problems related to word problems involving rational equations.